So we are going to start our morning session with talk. I'm just waiting for Desmond to get back to the back room, and we can start recording. Our first speaker in the morning is Radu Roiban, and he will talk about anomalous dimensions, strong coupling, next leading order and beyond.
So first I'd like to thank the organizers for the invitation to speak here. So this talk is, well, first of all, it was designed to be way longer than 40 minutes. And it's based on work done earlier this year with, okay. It's based on work done earlier this year with Cyclin, and as well as on work that will appear fairly soon. So as we've heard yesterday from Matthias, there's been a lot of progress in our quantitative understanding of the ADS-CFT correspondence, and especially as far as anomalous dimensions are concerned. And well, there were really two bits that entered into this. On the one hand, it's integrability, and on the other hand are twist operators. So twist operators will be important in this talk today. And especially we will try to understand exactly what their anomalous dimensions do at strong coupling, especially at this order. So to this end, I will begin with a particularly brief review of twist operators, which will largely rely on what Matthias said yesterday, as well as on their relations to classical solutions. Then, with this in mind, we shall proceed to understand how to compute their anomalous dimensions at strong coupling in terms of a worldsheet partition function in conformal gauge. Then, after a brief detour through the Green-Schwarz string, we shall be computing them. First, for twist 2 operators in the large spin limit, and then for the infinite twist in this particular double scaling limit. And then after all that, we shall proceed to the next speaker. So twist operators look like these. They typically have many fields and many derivatives. The number of fields is the twist. The number of derivatives is the spin. If we look at them from the standpoint of the gauge theory, then beyond 2 loops we know fairly little by explicit calculation. From the strong coupling end, actually also from the gauge theory, there were really 3 interesting limits that have been identified through the work of various people. The first one looks very much like the BMN limit, and at strong coupling the anomalous dimension looks like this, at least to leading order. Then the next limit is a double scaling limit, which looks like this, and at strong coupling the anomalous dimension should look like this, again to leading order. And last, but definitely not least, it's this other limit in which the spin is substantially larger than the twist, well, then the anomalous dimensions should scale like the logarithm of the spin. So to make contact with gauge theory, especially higher loop gauge theory, one really wants to keep j equals to 2 and take the large spin limit, case in which the anomalous dimension should look like this. And it's been known for a long time that well defined this way, this function f is the same as the anomaly of a null cusp-Wilson loop. Now, while this is what we want, this is what we can do, really. We need to take j large, not terribly fast, but still large, for the asymptotic beta answers to apply. So, well, the conjecture for which evidence is really accumulating is that this function f and this function f are really one and the same function. So the evidence for that starts from weak coupling and proceeds to strong coupling. And well, it really involves solving the BES equation. Now, let me skip the weak coupling part and proceed directly to the strong coupling, for which a solution, analytic and perturbative in 1 over square root of lambda, was constructed this year after, well, substantial work by various people, hopefully most of them listed there. So the solution looks like this, and we will hear much more of it from Kochemsky's talk. So the universal scaling function f looks like a standard expansion in 1 over square root of lambda. The first two coefficients, the blue guys, have been compared successfully with string theory calculations. The third guy is the subject of this talk, and the following infinitely many guys remain to be compared. We will need infinitely many graduate students to do that. Anyway, so if you look at this and you think that, well, really this has something to do with a two-dimensional field theory, and you look at the kind of numbers that appear here, and also depending upon your level of optimism, you can try to interpret what you see. And the interpretations range between a best case and the worst case scenarios. So, you know, transcendental numbers do typically appear in loop calculations. So if you stare at this for a second, you might wonder, well, what if all these transcendental numbers are really just loop integrals, and all these funny numbers are really just combinatorics? Well, this would be great if it were true. We don't know yet, really. The worst case scenario is that this is all a tangled mess, and after you shake it up for a while, then these things come up. Anyway, exactly what the story is at higher loops is not clear. We will see exactly how this term comes about. So this is the story as far as operators are concerned. As far as classical solutions are concerned, the story starts many years ago with a solution constructed initially by Gubser, Klebanov, and Polyakov, which sits in an ADS inside ADS5, which looks like this. You have a simple time component, a simple angular component, and some elliptic integrals for a third field. Now, one thing that I need to point out is that there is a natural parameter from the string standpoint, which is really this ratio, the spin over the square root of lambda, which is to be contrasted with just the spin, which is the natural variable from a gauge theory standpoint. Anyway, this solution is complicated, and you really don't want to deal with it as such, but it simplifies quite a lot in the scaling limit, in which really this third field becomes just linear, and well, strictly speaking, the string becomes a stick of length log s, and this stick spins with an angular moment, with an angular frequency, which is also log s, which is this omega there. So when all this is sort of cleaned up, the energy, or rather the difference between the energy and the spin, grows like log s, and this f here is the large spin limit of the twist 2 anomalous dimension. Now, you can read this in a different way too, basically as the zero twist limit, well, the twist limit, the twist equal 2 limit of another solution, which has non-trivial R charge equals to nu here. Now, in terms of this other solution, the energy, which is still a complicated function in general, is a function of 3 parameters, s over root lambda, j over root lambda, and root lambda. So as a function of 3 parameters, you can slice it and dice it in all sorts of directions. You can recover the universal scaling function. You can set j fixed and take s to infinity, and then recover the large spin limit of twist 2 anomalous dimension. And you can also take this double scaling limit and recover something that we don't know yet. But Matthias told us that there is a very nice equation at weak coupling, well, as a weak coupling expansion, which will produce this for us. Anyway, once you have this, you can play further games like expand in this ratio. And this prime should not be there. Anyhow, so this, as well as the solution on the previous page, are what we will be mostly interested in. So we would like to compute their energy from the worldsheet standpoint, and well, the question is how to do this. Well, you can proceed in very many different ways. But the main observation is that really these are solutions that carry some charges, and we would like to really know what these charges are. We would also like to make our life as easy as possible, and to that end, we'd like to break as few symmetries as possible. In particular, we don't really like to fix static gauges. So with that in mind, we would like to stick to conformal gauge and compute the energy, the space-time energy, in terms of something that is easy to compute in conformal gauge. Well, the easiest perhaps to do there is the partition function. So with that in mind, let's see how to compute space-time energies, well, energies in general, in terms of partition functions, and then proceed to the worldsheet partition function. So the idea is simple, and it goes back to Landau and Lifshitz book, page, I don't know, 100 something. So you start with something like a grand canonical partition function with a Hamiltonian and some charges and some chemical potentials, and then you compute the average charges. You can compute the average energy. They are related by this expression in the large volume limit and if interactions are local. And once you have all this stuff, you solve this for H, plug it back in here, and you're done. H is what you're looking for. Log Z you in principle know. H you know because you solve these, and Q is something that you can fix by hand to whatever you want. Now, so if you look at this setup, you note a few things. Well, first, what you put here in the exponent is not really the Hamiltonian of the system, but it's slightly modified. The second, which you notice if you think about it a little bit, is that you can take this and move it to a Lagrangian formalism, and then this looks very much like the original theory in a non-trivial background. That's just because charges typically are momenta corresponding to some fields. So in the Legendre transform to the Lagrangian formalism, you just shift the time derivatives of some fields, so you can absorb that by some linear background. And last, but definitely not least, the stress tensor of whatever theory you had starts depending on these chemical potentials. Well, first of all, because this is the 0,0 component of this modified theory, but you can go back to the Lagrangian and derive the stress tensor and find it. So, oops, never mind. So this is not really what we want. Well, at least it is what we want, but not exactly in this form. So we would like to interpret H as, well, as the worldsheet Hamiltonian, and Q as something else. Well, the observation is that the spacetime energy is, well, besides being the spacetime energy, is from the standpoint of the worldsheet theory one of the many conserved charges. So we can actually put it among these Qs with a chemical potential. Now, there is a small complication, which goes by the name of the Virasoro constraint, which says that, well, because the Hamiltonian depends on these, because the stress tensor depends on the chemical potentials, you can't really compute all these charges directly, because the chemical potentials are related by the requirement that the stress tensor vanishes. So you can compute fewer. Now, so you lose one of these parameters that were very useful. Now, you also use actually one average, which would be the average of the two-dimensional Hamiltonian, because that's also 0, because of, for the same reason, the Virasoro constraint. So you lose one parameter, you lose one average. So in principle, all this should still work in some form or another, and it does. So here is what you do if you looked just at a string with spin. So you pick the Hamiltonian, the undeformed Hamiltonian to be the two-dimensional one. You pick one charge to be this difference, just because this is parametrically smaller than either E or S. And then you don't have any charges to compute because the Virasoro constraint sets kappa to 1. We're left with one equation and one average, and the two are actually equal. Beta is really the length of the time direction, and because the solution is homogeneous, it actually cancels in this ratio, so we don't really need to worry about it. So this actually proves that the observation that really started with the work of Frolov, Terziev, and Zeitlin, that for single charge solutions, you can just compute the worldsheet partition function in a particular background and find the target space energy this way. Which one would be the second one? I mean, well, so it turns out that both T plus and T plus minus, well, both T naught node and T naught 1 are actually satisfied by setting kappa to 1 at the same time. So the same goes true if you want to add a second charge, except that it's slightly more complicated. So let me not go through it in detail. Just list the answer, which is this. Gamma would be the worldsheet effective action. Kappa is whatever the Virasoro constraint implies, which for this particular solution we looked at is just this, that kappa is the square root of 1 plus nu square. Now, the way to read this equation is as follows. You're supposed to take the second one, solve it for nu, and plug the result in the first. There is some square root of lambda dependence, which is hidden. It's really in the effective action. But besides this, everything should be fairly straightforward. You can take kappa, replace it in here. Things simplify a little bit, but not much. So the moral of this story is listed here. So to compute target space energies in this framework, you're supposed to take this modified Hamiltonian, compute the partition function with it. This is equivalent to computing the partition function in Lagrangian formats for the undeformed Lagrangian, in which besides whatever classical background you want to pick, you also pick this linear stuff, and then apply the equations on the previous slide. Clearly, if you remember the way the solution looks like, this setup is really tailor-made for whatever folded spinning strings we have, because they all have these linear backgrounds built in already. And HI, well, they used to be called kappa and nu there. So any questions? So the way to do the calculation involves, well, a way to do the calculation involves the Green-Schwarz string. And before proceeding, there are a couple of comments to be made. Well, the action typically looks like this, whether it's in ADS or elsewhere. So we want to expand in inverse string tension. You can read this in two different ways. First, you can read it as a closed string theory. And then you compute, you worry about classical solutions, their energies, and well, this has been successfully used and very efficiently used as input for the construction of the beta ansatz. Now, you can also read this as an open string theory, and then the questions are slightly different. You worry about expectation value of Wilson loops and things like this. Sometimes, not all the times, but sometimes, there is a very close relation between these two, as it turns out to be the case for twist 2 infinite spin operators. Well, in other situations, it turns out that you can sort of formally map one to the other. Basically, it's the same relation as in the case of infinite spin twist 2, except that you don't really give a Wilson loop interpretation to anything. All you do is you take this theory, you hit it with some invariances of the partition function, and you simplify things a little. So with that in mind, with those cryptic comments in mind, Let's go back to what happens at twist 2. As I was mentioning, we know from the work of Korczemski and Marchesini that they are related, well, that their anomalous dimension is related to the expectation value for cusp Wilson loop, like so. A2 would be the regularized area of that Wilson loop. So this was a field theory argument. Now, what about string theory? How does it work, at least in the framework that we've constructed? Well, so the standard prescription for a Wilson loop calculation would be this, whereas for single charge operators like these guys, we've argued that it should be something of this type. So if this relation is to hold, in string theory we really need that the open string partition function is the same as the closed string partition function. Therefore, the two solutions corresponding to twist 2 operators and the cusp Wilson loop should be related by something that leaves Z invariant. Damn it. So this turns out to actually be so. And to prove it, well, the proof looks like what you see on the slide. You go to global coordinates, you make some transformations, and well, some symmetry transformations. In particular, you do a Euclidean rotation, you do a series of 3 discrete SO4 2 rotations in these coordinates, and you can map the first set of 2 equations into the second set of 2 equations. So this we did with Korczemski, Terziu, and Zeitlin a while ago, and was also done by Aldea and Maldacena pretty much at the same time. So, so what we've learned is that also from a string theory perspective, we can just look at an open string setup, which would look like this. So if you project this that cusp Wilson loop solution to Poincaré coordinates, would look like this. The solution looks like this. So this was constructed by Korczemski a while ago. Now, the reason why I'm sticking to this metric will become clear shortly. So this looks, you can read this metric in 2 different ways, either a Z to 1 over Z transformation of a simple, well, of the standard Poincaré patch metric, or as the T-dual along this direction parallel to the boundary of the same metric. Well, eventually we will pick the second set of words, but well, that's 2 slides from now. So anyway, going back to the Green-Schwarz story. How much time do I have? Okay. Okay, so going back to the Green-Schwarz story, this would be how the action looks like, written in terms of the pieces of the left invariant 1 forms of this particular coset. So this theory has a gauge, has a local symmetry which requires fixing. Pretty much for any classical solution, you can find a gauge which is ghost-free and natural in some sense. Well, we will take the open string perspective, and that, well, we don't really need to worry too much about that because a very nice gauge was constructed years ago by Kalosh and Zeitlin. So there are a number of features that any Green-Schwarz calculation in any, well, loop calculation, I mean, in any background has, and most of them are unfortunate. But I would like to draw your attention to just a couple of these. In particular, after gauge fixing, the theory is, at least around some classical solution, the theory is divergent by power counting because during gauge fixing you necessarily introduce a dimensionful parameter. So from that standpoint, for the theory to make sense, it is necessary that it is finite, pretty much like gravity. There are formal arguments for finiteness, but well, they can go wrong in very many different ways, especially because of regularization. One needs to pick a regularization which preserves all the classical symmetries of the theory. So with these comments in mind, let's go back to the calculation and the words I said 30 seconds ago. So we had this metric in terms of which the Wilson loop solution looked like this. So we can read this in two different ways, either the T-dual of this metric or this coordinate transformation of the same metric. Both sets of words lead to a Green-Schwarz action, or at least can be completed to a Green-Schwarz action. We will pick the first set because it leads to a simple action, namely this. The reason why this is a good thing to do is that first, the action fits on one line. Second, because it's quadratic in fermions, and that's not because I've omitted the higher order terms. And, well, because the calculation is easier. So with this in mind, we take this solution, we plug it in here, we expand in fluctuations around it, and compute. Well, the leading term of that operation leads to the first term in the expansion of the partition function and of the target space energy of this particular solution, and it turns out to be 1, as was known for many years. The second term, A1, is a difference between two determinants, the determinants of the kinetic operators that come out of the action on the previous slides. Then they look like these. Some free terms, some more free terms, some tangled terms. And well, when you compute the determinant, you find that you have a collection of massless modes, 2 modes of mass square root of 2 and 1 mode of mass 2. And then the fermions have all equal masses, and the mass would be equal to 1. So when you compute this, you find the famous -3 log 2, where the pi was pulled out. So this recovers, again, a known result. So the next term is slightly more complicated. For the first time, we actually need to pick a regularization scheme, and as I was mentioning, it has to be a regularization scheme that does not break classical symmetries, in particular kappa symmetry. Now, kappa symmetry, as it turns out, has a self-dual parameter, so it doesn't want to be moved off 2 dimensions. So we need to stick to 2 dimensions. So the regularization will be the following. We don't regularize. We don't regularize and really rely on the spontaneously broken conformal invariance to take care of all the logarithmic divergences for us. If this doesn't happen, we're in trouble. It will happen. Now, there will be, so all that can be left after this are power-like divergences, which can be regularized away at the end in any number of different ways. And if you're really, really careful, you can start including the contributions of the measure of the path integral and of whatever algebraic ghosts you find from the kappa symmetry gauge fixing, and then they should all go away. But we will not take the second route. We will regularize them away by basically dimensionally continuing the final integrand away from 2 dimensions. Now, this sounds very peculiar, and it is bound to go wrong if you are in any random quantum field theory, especially because the words final integrand make no sense there. But here it turns out to be possible to split up everything into integrals with power divergence with no subleading ones, log ones which go away, and finite pieces. So as it turns out, there is, well, perhaps the nicest feature of this regularization is that it preserves the BPS nature of the BMN string, as we showed earlier this year. And this really would not be the case if you just use dimensional regularization. Anyhow, so take that action, expand it to cubic and quartic order. You've got all sorts of funny vertices, which depend on the various constant vectors, which I didn't point out, but were there in this Wilson loop solution. They really parameterize the null directions of the Wilson loop. And you have really 2 topologies to worry about. Each of these lines can be bosons or fermions, up to the fact that here you can't have 3 fermion lines.
When you say you rely on broken conformal invariance to take care of the logarithms, I mean, you have some massless
yeah, they will.
You don't get infrared divergences
No.
when those massless propagators appear in the.
No, they all take care of themselves.
It's all.
So let's see. So you compute, you can try to do this by hand, but the easiest thing to do is to stick it in the computer, and this is what you get for about half of the calculation. Now I should have provided magnifying glasses, and if I did, then this is what you see for any one term. So you have a collection of standard propagators and some numerator factors which depend on the constant vectors. So the reason I chose to magnify this particular term is that this is really, well, it is almost the single term that survives once everything is cleaned up. Anyway, so the way to deal with these integrals is to treat them as tensor integrals in 2 dimensions and then reduce them using the fact that the denominators, not only this one, but all denominators here, are actually Lorentz invariant. So you use tricks of this type, which are well known in the business of computing scattering amplitudes, as well as partial fractioning. So, well, I won't show you exactly which term cancels which term, but all divergences do cancel out. They do cancel out actually in a fairly non-trivial way. Well, not as non-trivial as it could have been, but never mind that. So it is also worth saying that they would not have cancelled in dimensional regularization. There would have been first a divergence and then a finite part that would have been left behind. So here is the answer. You've got a purely bosonic contribution and a mixed contribution. The first term comes from this topology with 3 bosons. The second one with this topology with 4 bosons. So you've got this finite piece, which is given by the Catalan number, and a divergent term, which is logarithmically divergent, only in the UV. The IR takes care of himself. Thanks. And then this other bit gives you basically the same divergence, just with the other sign. And well, when you add them up, they all cancel out. The fermions are actually very nice, as it turns out, due to the choice of action, but that's a separate story. So you find basically the same Catalan number, and well, when you add it up, you find what the BS equation said. So this is the answer for the first part. In the remaining part of the talk, okay, so so what we found was evidence at strong coupling that the universal scaling function is the same as the cusp anomalous dimension, which provides by itself a strong support for the conjecture of this matrix and the beta ansatz, even though in this particular regime there are problems that Matthias emphasized yesterday. Well, not problems as problems, but more like conceptual problems, why it works at all. Anyway, so this is the story at 2 loops. So one might wonder exactly whether there is any point in going to higher loops, whether it tests anything. And actually it does. So at 3 loops you find the first Feynman diagrams, which contain both ADS and S5 fluctuations. So one might wonder whether something funny happens because of that. At 4 loops is the first place where this, well, where a more non-trivial version of the Catalan number will appear. At 5 loops, you find the first non-planar vacuum diagram, which, according to some wisdom, might actually cause a jump in transcendentality. Anyway, what to expect is really hard to tell. So since I have only 5 minutes left, let me skip that part and proceed straight to including twist. So including twist, in particular large twist, turns out to be remarkably similar to the calculation I've just described. The solution, at least as a closed string solution I described in the first few slides, if you apply basically the same coordinate transformations to that solution, you find something that looks like this in the Poincaré patch framework. Now, in principle, you should just take this, plug it in the same action, expand, and basically do the same steps. There are, of course, technical complications, as it always happens when you add things to something that works already. And the main technical complication is that the propagators become Lorentz violating. They become Lorentz invariant if we expand in this nu. So this is really what we will do. So we will expand in this nu, which is the same as expanding in this L. There is a subtlety. Once you do that, you find infrared divergences. So you have to be careful to keep track of them and not overcount them. These divergences actually don't come from the they don't come at all from the S5 sigma model partition function, which turns out to be identically 0. They come from diagrams with S5 bosons and 2 fermions, which are computable. I was about to say easily computable, but let me just say they are computable. So once you set up the calculation, you're again supposed to find gamma, plug it in this set of equations, eliminate L hat between them. And this is what you find. So once you eliminate L hat, you end up replacing it with this particular ratio, which is the same as little j over square root of lambda, where little j was introduced by Matthias yesterday. It's just the natural gauge theory ratio between j and log s. So anyway, you find to leading order something that was known since Frolov and Zeitlin's work. Then for the first term, you find something that was known since December last year from the work of Frolov, Terzio, and Zeitlin. And then you find the new stuff, which is, well, the leading L-square correction to the universal scaling function, which looks like this. So there is some funny structure appearing here, but the bottom line is that it agrees with a conjecture based on the 06 model of Aldea and Maldacena. So there are really 2 log terms here, and they come out from very different sources. In particular, the leading one has nothing to do with a 2-loop calculation. It's really there because of this operation, because of solving this and plugging the result in the first equation. And the second coefficient here, which is -6, receives actually contributions from 2 sources. One is the same operation as before, and the second one is actually a result of a straight 2-loop calculation. And the colors, well, I guess you can't tell them apart. So my time is up. So here's what we've done. So the conclusion should be that the Green-Schwarz makes sense at 2 loops in this particular regularization that I've tried to outline. We've computed the cusp anomalous dimension at strong coupling to 2 loops and found that it agrees with the BES equation, the predictions of the BES equations. So it strengthens the fact that the universal scaling function and the large spin limit of twist 2 anomalous dimensions are essentially the same. It is technically accessible to compute the 3-loop cusp anomaly and essentially push this comparison 1 step further. In the process of doing this, we've set up a way of computing the anomalous dimensions, or the energies of multi-spin strings at strong coupling. And in this computation, the charge what might be called charge normalization plays an important role. By this I mean a correction to the relation between solutions of the equations of motion on the worldsheet and conserved charges, something like this. And we've also found the 2-loop correction to the leading 2-loop correction, which includes this parameter that appears in the double scaling limit. And well, it is in principle possible to compute further corrections to this. So thank you very much.
Expression for this F2?
No.
Or you?
Yeah, well, I mean, we could compute L to the 4th, L to the 6th corrections. In principle, my computer might give out at some point, but.
So I can ask
I mean,
you if I need one particular one.
Okay, so, well, I mean, I
I
can.
mean, how far can you go?
How far can I get?
I mean, you don't have a closed expression like for F1.
No, no,
room
no.
for that.
I mean, the reason such an expression is fairly prohibitive is this.
Yeah.
Is this. I mean, you end up dealing with about 50,000 of integrals, including, with denominators of this type. So, as far as I can tell, there is no structure that can be noticed in these integrals. So, they have to be computed one by one. Of course, numerically, I can get an answer. I could get a plot, for example, with a fair amount of work. Yeah.
Nathan?
Okay. If I understood correctly, the logarithmic divergences cancel without the fermion. Is that true?
Yes, they cancel separately, actually.
Do you have an explanation of that?
Yes, to some extent. So the way it works, at least, so I have no explanation what I could conjecture what happens at higher loops, but at 2 loops it works like this. If you use dimensional regularization in, say, a bosonic sigma model, there is a log divergence that comes out as a 1 over epsilon square times order epsilon, where the order epsilon term in the numerator comes from some algebra, and the 1 over epsilon square is basically the contribution of a double bubble like this. So it turns out that this order epsilon term in the numerator just goes away in this particular regularization. That's the best explanation I can come up with. So it implies that in this regularization, the 2-loop beta function of the bosonic sigma model vanishes.
It's just a clever regularization.
Yeah. Well, it is clever, but it's actually clever because of the fermions, because they don't like anything else, apparently.
Isn't the beta function supposed to be scheme independent up to 2 loops?
In a gauge theory, yes. In a sigma model on a space of this type, no. It's
Only the
very-
1 loop
yeah.
one.
One last question.
The Alderman percent conjecture also contains the matching scale between the 6,
Yes.
which contains some gamma 1/4.
Yes.
But are you consistent with that?
Well, so there is really a physical difference between the 06 sigma model by itself and the 06 sigma model inside ADS5. And the physical difference is that the first one has a scale, whereas the second one has no scale. So there is no scale that I can match with. So the 06 sigma model confines and it generates the scale, whereas this one it simply doesn't because it's a conformal field here.
So this funny gamma function shouldn't, the mass cap of the 06 model shouldn't appear here.
No, they shouldn't. I mean, if you wish, they are encoded in this particular -2, which is really the 2-loop contribution.
It'll be exponentially suppressed in the coupling, right? If you look at the mass gap of the 06 sigma model would be something like e to the minus square root lambda. So you'd expect these effects to show up as non-perturbative corrections to the series that we're thinking about.
Well, one could take this standpoint, but I mean, really, if such corrections exist, then they really have a totally different origin than they have in the 06 sigma model. Just because this theory, I mean, Green-Schwarz in ADS doesn't confine, even though it has a piece in it, which if you take it out, it does confine. So if you wish, you can think of the 06 sigma model by itself.
How do you know it doesn't confine? I mean, in the infrared, it
It's-
looks
it's
like an
conformal.
06 sigma model, and it's an infrared effect,
Well,
right? The confinement. So.
I mean, we can debate that afterwards.
Can we stop with Radu thank him again.